I don't know if there are any questions before I start. I did change I mean, because some people may have joined the course this week. I don't know if you noticed that I think at some point on the weekend I got posted like a mini quiz or mini assignment. I don't know how it's called on Canvas. But I changed, I mean, if you didn't do it, I just changed the deadline. So you have like, it was very short. It was just for you to like get acquainted with this formula that I wrote last time. But if you haven't done that, then you can just uh, finish it. I think I gave you until Wednesday. Uh, uh, Evening, so that should be enough time. I think it takes like 5 minutes to do. Um, so let me remind you the last thing I wrote last week. So if you had a vector, which again for us, they are always drawn at the origin. So since a vector it starts at the origin, wherever it ends, that's how we will refer to it. So in this example, the green vector, it finishes at the point x comma y. Okay, and the idea of a rotation is that you can take that vector and rotate it counterclockwise by an angle theta, right? And once you do that, you produce a new vector. We don't know what that vector is, so I'll just call it v sub r. So its new entries are x sub r, y sub r. Again, here the r starts for rotation. And what we were doing last time was just trying to find like a formula that would give you the entries of the new vector in terms of the old one and the angle of rotation. So if you remember, the key besides like using some trig identities, like the other key input that you have to do in order to find the formula was use the fact that if you have a rotation, right, when you rotate a vector, then the length of that vector would not change, right? Like the length remains the same. And that kind of meant when we did this right triangle that the hypotenuses were the same. And after that, it was like, again, like about the trig. Okay. So I thought that first, before like telling you how is this, where do matrices appear here, I should just show you like a quick animation. Okay. So this is algebra. I don't know if how many of you have used it before, but it's kind of convenient. So here is a vector, the red one, whose entries are x and y. So I'm allowed to, I created like a slider. So if you want it, if I want, I can also vary the entries separately, right? So here I'm changing the horizontal component and now I'm changing the vertical component of the vector, right? And then I choose an angle theta. It's kind of just annoying to call it theta on the computer. So I just called the angle T. It's just easier for me. So I called the angle T of rotation that can go from 0 degrees to 360 degrees, right? And then there's this new vector, which is a rotated vector. So for example, let's say that the angle of rotation, I want it to be, let's something small, like close to 30 degrees. So the rotated version is somewhere in there. Okay, and in fact, like if you check the entries, like the entries for Q, you'll see that it is using this formula of cosine with something cosine minus something sine, and then something sine plus something cosine. It's just that, again, on algebra, I had to use A and B instead of X and Y. That's where everything worked out. But it's exactly the same formula that you see here if you change like the corresponding symbols for the variables. Okay. And so if you start varying there, if you start, okay, so if you choose theta to be 0, right, or a 0-degree rotation, like nothing happened, right? Like that kind of makes sense. Like the old vectors and the new vector just happen to coincide. So that's why you see them pointing in the same direction. They're exactly the same. And then you just like start increasing theta little by little. until you, I mean, as much as you want until you get to 360 and then you're back where you started, right? So also, I thought it was useful to show you this animation because sometimes when I do these pictures to find the formula, like I kind of draw everything on the first quadrant just because it's psychologically easier for everyone to like to see the formulas on the first quadrant. But this formula for the rotation is supposed to work regardless of where the vector started, right? It could have started the first, second, third, or fourth quadrant, and the angle could have been anything from 0 to 2 pi radians, and this formula still works. Okay. So that's what makes in particular the formula useful. Um, there's no good formula that would only work for like things on the first quadrant, for example. Like the formulas are supposed to should work for like a vector regardless of where you draw it. And I mean, if you think about this, like practically, rotating is kind of useful to have formula for a rotation because then you have like a 3D object, right? And then you could, I mean, there are like analogs of how to like formulas that tell you how to rotate a 3D object, and you can imagine that being useful. Well, like on the fun side of things, like just like for video games, right? Like how do you rotate like a camera on a video game, like the player's point of view? So there must be a formula for that, but also like flight simulations, like almost everything involves like some sort of rotation, right, in real life. So like whenever you move, you're rotating constantly. So it is useful that there's a formula for those rotations, and also that they can be found. I mean, you'll see in a second that they can be found using matrices, which is what makes it connects that to this course. But I thought I should show you first this animation to just emphasize that really this works for all angles for any vector you start with. Okay, so let me stop sharing. And now we don't need this. I don't think I will use the computer anymore, so okay. I think most of the board can be seen here. Yes, not this. Okay, so we have these two equations. You can think of those so we have two equations, and you can think of x and y as kind of things that you control, right? Because it's kind of like the initial vectors you start with. So they're kind of two variables or that are your control, right? And the two variables together with your choice of angle fixes completely the new vector, right? So 2 times 2, so two equations times two unknowns, 2 times 2 equals 4, right? So what's convenient, like just a way to think about this is to extra, like, keep track of this data in a slightly different way. So that's where like a matrix comes in. So the system of equations, what you can associate is a matrix. So you associate this as a matrix. Let's call this matrix R for rotation. So the first equation, right? The numbers or coefficients or like things multiplying x and y, they just become the first entries of the first row of the matrix. So you have something like this: cosine of theta minus sine of theta. So it's fine. Like first, so this is first row corresponds to like the coefficients that appear in the first equation. So and then second row. second row, you read off the coefficients multiplying x and y. So the first thing we see is sine of theta. Let me see if I change the. And then you see cosine of theta. Right? So second row of the matrix has to do with the coefficients that appear in the second equation. So you can think of that you were doing like an operation on a vector, like rotating it, and that information is being stored or encoded by this matrix that has like all this data of what's going to happen to each of the variables x and y. Is that making sense? Any questions about this? So in general, the idea of a matrix, like which later will be called like a 2 by 2 matrix, but right now I'm just calling it like a matrix. So like a matrix, like A equals A. Let me use the same color actually. So B EB. Right, if someone writes like an array like this, where here A, B, C, D are numbers. Well, what that means is that, again, you should think of this as a sort of like conversion mechanism. So it's going to convert the vector x comma y into a new vector. So it turns a vector B with entries x, y into a new vector with entries so what should the entries of the new vector be? Well, again, the first row has kind of to do with the first equation or the first entry. So this will be, this is like thing that was multiplying x. So it will be ax plus by. And then the second row had to do with the second equation or the second entry of the vector. So that would be Ex plus by. And like basically what we have to do today is just well, get used to this way of thinking about the operation of the vector and like different ways you can write it that make it faster to memorize or like to use in practice. Okay. So we'll spend most of the today's lecture just like trying to understand a little bit better what this is what's going on here. So for example, let's try to do something very concrete. Let's say that the matrix I gave you had been 1, -1, and then 1, 1. So the idea, what is this matrix supposed to do? So it takes the vector xy, and we'll produce, well, let's try just to think about that. Again, like the coefficient, these numbers are kind of the numbers that are multiplying the x and the y's, right? So 1x minus 1 y, and then 1x plus 1. It's kind of nasty to have all the numbers once written out explicitly, right? So you just write this as x minus y, comma x plus y. Right? That making sense? So this is a matrix. Like if you thought about what's going on here, what this is doing is like it takes a vector and subtract the entries, and that becomes a new entry of a new vector, right? And also adds them up together. So it's kind of like doing subtraction and addition at the same time, right? It's kind of like a way to store subtracting numbers and adding numbers together. So just to make this more concrete, like what this says is like, for example, the vector 3, 5, right, goes to what? 3 minus 5 would be -2, and 3 plus 5 would be 8, right? So if you wanted like to do like, write a computer program that literally like takes the difference of two numbers and add them together, like a very elegant way to do that would be in terms of like a matrix, right? Because it's kind of doing like both operations at the same time, right? Instead of like just writing two lines of code like separately, if you know what I mean. Is that making sense? So again, you should think of matrices as just like ways to store instructions or operations that will occur that would happen to vectors. Okay. Let's do another one that's it looks kind of a lot easier, but it actually useful to keep in mind. So here's another example of what you could do with a vector. Imagine that I had a vector, again, xy, and I put a mirror along the x-axis. So now there's going to be a mirror here. So I want to see like find a reflection of this vector with respect to this mirror. So let's call this V sub m, m for mirror now, right? And well, it's kind of hopefully it's somewhat easier. What are the entries of this new vector in terms of the original? What's the first entry? It's just x, right? Nothing happened to the first entry. And what happens to the second entry? It's just negative y. Good. So it just flips, right? Changes the second entry, this reflection. And that seems like a relatively easy operation, right? Like, and this looks a little bit of an overkill right now, but what is x? X is 1 times x plus 0 times y, right? So, is that making sense? 1x plus 0y gives you x, right? And what is negative y? Negative y is 0x minus 1 times y, right? Well, first, let me give you a second to copy this. Is that okay? why would I do this? Because what it tells you is that there's secretly a matrix hidden here, right? So what the matrix, we could call it M for mirror, like the mirror matrix. I mean, actually, what we call like R for reflection, but like R is kind of being already used for rotation, so it would be like a mess. So I'll call it M for mirror, and like 1, 0, 0, -1. Is that okay? So even like when you have a phone and you have like take a picture, but then you want to rotate it on your like your cell phone, right? Like the rotation. I mean, well, you could rotate it using that, but sometimes you also just want to reflect it, right? The reflection also can be encoded via matrix. That's what I'm trying to say. And like I mean, it's maybe again, this is a good example because it's kind of too simple. But even when it's too simple, look, there's like it's hidden in there, like because the bunch of zeros like kind of makes it less clear that you could have written it down as a 2 by 2 matrix. But and again, I'll explain in a second why I'm calling it 2 by 2. But all that I'm trying to say is that um, there are operations that you can do on vectors that are very conveniently stored um, in terms of matrices. Any questions so far? And in fact, like I'll ask you later, like it's a fun game, like I'll just give you like an operation of vectors, like can you find the matrix that does that, right? It's kind of like a good thing to become acquainted with. Okay, now, so that's kind of like the basics of how you're supposed to think about these matrices. Now what I'm going to do is kind of rewrite this in a way that's more traditional, and that's like to make it like more like, to make it faster, like how do you find like the new vector that you get when you apply the matrix. So here's how you should think about what we're doing. Yeah, what you should think is happening is that you had this vector which had entries x, y, right? And you kind of apply or like running, like you put it through like a machine or like a process, right? Like which is the matrix A. So think of the matrix A as some sort of process. Right? And it spits out a new vector, right? That's what we have been doing so far. So you started with a vector like 3, 5, you get -2, 8. And here you started with x, y, you get x comma -y. So you're running, the input is some vector, the output is a new vector, right? So now we're getting a vector, which, again, if you compare it with the formula, it's just ax plus by, bx plus by. Okay. Now, since it's a vector, you want to give it a name, right? Before it was called v. Now you're going to call it something new because it's a new vector in general. But you don't want to give it like just like a random name because otherwise like it's not like it won't be too useful. So it's kind of like the best possible name would be one that takes into account the name of the original vector and the name of the process that you applied to it, right? So it's well, the easiest thing to do is just call it A times B, and that's what like the name that we stick with. So this is what will be the name that we give to this new vector. So it is written so that it looks like as a multiplication. So that's kind of like the idea behind it. So you should think of it like, oh, you're multiplying the matrix times this vector. And this will be even more precise in a second. But right now it's kind of like you're like, well, first name, last name, right? Like it's you're baptizing this vector. Like you had to put it, like you had to put like something that was useful. And this kind of makes sense. Okay. But in fact, to make it even better, and that's now like to actually take it more seriously this idea that it looks like a multiplication, like what we do to memorize the formula. So to make it seem more like a multiplication, multiplication of a vector with a of a matrix with a vector. Well, the first thing that you do is actually rewrite, instead of writing the vector horizontally, you write it vertically. So you write the vector vertically. So now what I mean by that is that instead of writing x and then y, you write x and then below it y. I mean, they're really kind of like the same vector. It's just like you'll see in a second why this is convenient. And again, you run through the matrix process. And it spits out this vector that we're calling AB. But now, if you think about it, A is just like this thing that I wrote, A, B, C, B. And then D is this Y. The reason why this looks better is like, if you imagine you were typing this on a document or whatever, now that you're using the same number of lines or rows on your document, right? So they look more of the same size, if you know what I mean. And what I'm saying is that what we're doing secretly is that whenever we see this matrix with this vector, we're producing a new vector, which is like the one that I have been writing all this time, but just again, write this there. So in this example, like in our previous example, where we had like this different sum matrix, what I'm trying to say is that if you take 1, -1, 1, 1, with this vector 3, 5, which I'm now writing vertically, or it's also called like a column vector, these should spit out -2, 8. Okay, so it's essentially what we just did, but thought of a totally different way, because now you're thinking like, oh, you multiply this matrix with this vector, and that's what produced this new vector. So it's kind of written down so that it looks like multiplication, but it's like just because it's convenient that to set it up that way, for reasons that we don't get into. But like this is why it's called matrix multiplication with. I mean, this is why this is called multiplication of a matrix with a vector. So. Or like the other one that we just did would have been that, this mirror matrix, if you take 1, 0, 0, -1, and you multiply it, or like just like apply this process to x, y, you got x -y, right? So I'm just doing like, it's kind of like it saves you space, but instead of saying like, well, you take a vector 3, 5 to -2, 8, you just write this vector times this matrix gives you this vector. It's like a shorthand way of saying all of that. Or this vector times its matrix, sorry, this vector times its matrix gives you this vector, or this vector times this matrix gives that vector. But it's essentially that it, like this vector is being converted into this vector using this matrix. That's the same for the second one. Okay, yes.
So let's have to write the transformation of what a vector that's not going to different.
Right, like the convent, like so it is kind of like the convention is so that the transformation comes before the vector. Like the reason for that is like if you remember, well, I mean, for those who have seen like calculus or pre-calculus, right? If you write something like f of x equals x squared, right? In this diagram version, you can think, well, that just meant that you had like the input x, right? And you apply it through the squaring process, like you don't even give a name for that, but you call this squaring, right? And you get x squared. So like that's what, and then you end up writing f of x equals x squared, right? And there's actually a sense in which you could think of this as some sort of function, but that's not a point of view we take in the class, but those are called linear transformations. So like the reason why it's wrong, what I'm trying to say is like the reason why this matrix comes to the left is that because in pre-calculus or calculus, the function also comes to the left of the input, if that makes sense. So it's kind of like so that this notation like and this notation like you know, there's almost no difference between writing this versus a of b. If you write it this way, it looks more like a function, right? And it is kind of like really what's going on. So it's just a little bit more complicated to think about it for now, for us this in this way. But that's essentially the main reason why it's done this way, because like the functions, the name for the function comes before, well, comes to the left of the variables. Okay. Is that okay? So that was just an aside. It's not something to worry about, but yeah, like the vector kind of always is at the rightmost place in your sentence or like when you write it down. Because that's essentially what happens with functions. Any other questions? And it's like, yeah, it's cool to like find matrices that do the certain operations. So I'll ask you to do those. Like for example, find a matrix that flips, like that makes the x the first entry, the second entry, the first entry, the second entry, and the second entry, the first entry, right? Like that flips like the order of the entry, and that's like a flip operation and things like that. And that's what gets used like when designing circuits and logical systems or stuff like that. So it's like a fun good things you can do with matrices. But yeah, for now, what I want to teach you or like spend more time is just on how to think about this like in a convenient way. So how should we think about how to find a times b in a like in an efficient way? How to find or something that's easy to memorize, right? Or easy to memorize. And for that, we have to do a tiny detour into the dot product of two vectors. So let me tell you about that. But which, by the way, we'll do a talk about way more towards the end of the course. But for now, it's just a formula that's convenient to have around. So I'll just tell you what it is. So let's talk about the dot product of vectors. So just as an example, imagine, well, or just in the case of vectors of size 2, size of 2 vectors. Imagine I give you a vector which we would call u. It has 2 entries because it's size 2, so I'll call the entries u1 and u2. And I give you another vector which is v, which is v1, v2. So those are the entries of the 2 vectors. And the dot product is supposed to be what? Well, in order to find the dot product, what you do, and this is why I kind of like put one exactly below the other, you multiply their corresponding entries, and then you add up the answers. So like the first entry with the first entry gets multiplied. So you do u1, v1. And then you do the second entry with the second entry, multiply this together, and then you add up the results. But what I'm trying to say is that what we're doing here is like you multiply the corresponding entries of the vectors. And then add the result. Add this product. I mean, the parenthesis is kind of not needed here, but it's just to emphasize that you do one product, then you do another product, and then you add them together. So, for example, what if I had given you u with a vector 1, -1, and b with a vector 3, 5. So what is u dot v? Again, first with first, that's 1 times 3, right? Second with second is -1 times 5. And then you add them together. So this gives you 3 minus 5. And this gives you -2, right? No, I didn't choose these vectors randomly, right? Where do we see 1, -1 on this board? And where is 3, 5 on the board is here, right? So what I'll write in a second is that this entry -2, you can also think of as the dot product between this vector and this vector. Okay, and that is kind of like a useful way to remember like how to do this multiplication. I'll write this in a moment, but I'm just saying that this is kind of, I mean, in fact, like if you do it for the second row, like if you take this row and think of it as a vector, the vector 1, 1. If you do the dot product between 1, 1 and 3, 5, it is just 1 times 3, which is 3, 1 times 5, which is 5, 3 plus 5 is 8. So that's how you end up getting also the correct answer for the second entry. But before writing that down, well, first, are there any questions on how to do this? Okay, this formula for the dot product actually does work not just when the vectors have size 2. It can work for vectors of any size. The only requirement is that they have the same number of entries. Okay, so so this formula works. I mean, the formula for the dot product, or can be defined or can be found for vectors with more entries, provided they have the same size. As long as they have the same number of entries. So, for example, like again, just to pick up some random numbers or entries. If I am giving you a vector which is like 1, 2, -1, 4, and a vector v. Now this one has 4 entries, so like if I want to do like some sort of dot product, and this one better have 4 entries. So let's say 0, 1, 3, -1. Again, they're completely random numbers, but just to do something concrete. So what is u dot v here? Well, first with first, right? So it's 1 times 0. Second with second is 2 times 1. -1 with 3. And then 4 with -1. Right, so this one gives you 0 plus 2 minus 3 minus 4, and then what? It's -5. So this dot product happens to be -5. And if you, again, like dot product is something you will see from time to time in different classes, like in your physics classes, multivariable calculus, in statistics as well, or like, I mean, it shows up in many different places. Here, the way it's appearing is that the entries of the new vector are literally just dot products. So let me write that down because that's important to notice. So here's like an important observation. The entries of the vector AB are simply the dot products can be found by taking the dot product between the rows of the matrix and the vector B. So what I'm trying to say is that if A was like A, B, C, D, and B was X1, the entry of this first new vector is the dot product between the row 1 of the matrix with the vector B. And the second entry of this vector would be the dot product between the second row of the matrix and the vector B. So the new vector is found by, it's like a vector of dot products in that sense, like because you just find a bunch of dot products and what you get become the entries of the new vector. Does that make sense? Okay, so now we have to. So far, I have stuck to like the case where the vector has two entries, but in fact, you can kind of do something similar regardless of the size of the vector. So like that's what I need to tell you right now. For that, I just have to introduce a little bit more of like terminology involving matrices. So what's like what's the general case or like the general formula for? I mean, it's still going to be the same, but so let's just so case of AX or AB for I think the general when B is let's just say let me write this like that. Yeah, there's general case for finding A. Okay. So in general, A is going to be what we call like M times N matrix. So in general, M will A will be M times N matrix. And let's think about what that means. So M refers here to the number of rows of the matrix. And N refers to the number of columns of the matrix. So for example, if I write like the mirror matrix or this a different sum matrix. If I write this one, it's like two rows, right? One row, second row, two columns, first column, second column. So this would be like a 2 by 2 matrix. But you could also have something like this. So what would this be? It would be a 2 times 3 matrix, right? Two rows, three columns. And what would be something like the opposite can happen, so you could have more rows than columns, so you could do something. So this would be a 4 times 3 matrix, right? Is that making sense? So, I mean, just when you read this matrix notation, this is kind of universal that like that's how you should read it. But this is always number of rows followed by the number of columns. Okay. And it is a good name for this because like the number of entries each matrix has is literally the number, like the product of these two numbers, right? So this one has 4 entries. This one requires 6 entries, right? And this one requires what? It requires 12 entries. So an m times n matrix has n numbers, right? So this one has n h entries. Is that okay? Is that making sense? Any questions? Okay, so for example, here, for this one that I have given you, well, this will be a 2 by 2 matrix, right? And this vector, I mean, this is like a vector, right? But you can think of it as kind of like a special case of a matrix, right? Where it has like 2 rows and just 1 column, right? So you can write it as 2 by 1. It's kind of convenient to do this way. And what I was producing before, it was negative 2, 8, right? And this is producing another vector of with 2 entries, so this was producing a 2 by 1. Okay, so the idea is that in general, like something similar like, can still happens, but we just have to be keep more track of the sizes of the letters. So or the number of rows and columns. So now I have a matrix which is A, which is m times n, right? I'm going to try to multiply it by a vector b. Now, what should this be? Is actually going to be the same as before. So it's literally, it should be the same as the row, the products of the rows with the vector. So we do want that formula to continue working regardless of the size of the matrix. So it should be the first row dot the second vector, right? Or sorry, dot the vector b. The second row dot the vector b. And if he had like 4 rows, it would be row 3 dot b up to row 4 dot b. So this keeps going until you get to row m dot b. Is that making sense? But in order to do the dot products, right, it better be the case that these rows have the same size as the vector, right? Like we cannot do the dot product unless then, the size of this row or this vector is the same as the size of b. Like they should have the same entries, right? But what is the number of entries of the vector is is kind of the same, like the first number that you see here, right? Because a vector is always like one column. So like for a vector it's always one at the end. Because it's like we're thinking of it as a column vector. So what I'm trying to say is that first number you should put here is n, so that they match. Because I'm saying that the number of entries of the row it would be the same as the number of entries of the vector. Is that making sense? So let me put that like with a different color to emphasize it. So the idea is like this multiplication only makes sense when the number of columns of the matrix equals the number of entries of the vector. So let me write that down in words. So AB only makes sense when the number of columns of A equals the number of entries of the vector. Is that okay? And again, this is supposed to produce a vector, right? So this is going to be a new vector. So since this is going to be a new vector, it's just like a single column. That's why I'm going to put a 1 at the end. But then we have to think about how many entries am I putting in this new vector, right? So how many entries is this new vector going to have? We finish at row M, right? There's one entry per row of the matrix. So this actually can be allowed to be M. So let me, this will be M. So let me just put like a color to match them together. So what I'm saying is that you can, like the way in which this is defined is that you can multiply a matrix of a different bigger than 2 by 2 with a vector. And the sizes are not completely arbitrary. The condition is just that the number of columns match the number of entries of the vector. So let me do this for a concrete example so that it's easier to digest. So well, imagine that I had taken this matrix in the middle, right? Like this is 2 by 3. So let's go next. So I do 1, 2, -1, 3, 4, 5. So this is 2 by 3, right? And if you follow what I just wrote, the vector that I put here has to have the same number as columns. So this one had 3 columns. So the vector that I put here has to be 3 by 1. So what would be a vector, a 3 by 1 vector? I mean, we can do one that's easy, like 1, 0, -1, just for example. You have something easy to compute. So, and if like the way you should think about it is like when you multiply these things, like the threes kind of like cancel one another, right? So you forget about the numbers in the middle, you just keep the exterior numbers, right? So you get like you keep the 2 and the 1. So like whatever this is, it's going to have these 2 by 1. So it means that it only has 2 entries, which makes sense because there are only 2 rows, so there are only 2 dot products you could actually make. So maybe I will need a little bit more space here. So space. So if you do the dot product of the first row with the vector, you get 1 times 1 plus 2 times 0 plus -1 times -1. So that's the first dot product, right? And then the second dot product is 3 times 1 plus 4 times 0 plus 5. And this gives you what? One, well, this goes away. Then this gives you one as well, so it gives you two. And this gives you three. This one goes away. And then three minus five gives you negative. So this is the vector two negative. Is that okay? So again, if you think about it as a process, right? Like if you want to do this diagram again, like what this is like diagrammatically what's happening is like the input was this vector 1 0 negative 1. You run it through the machine A, which was this matrix 1 2 negative 1 3 4 5. Right, and it spits out this new vector, which is 2 negative 2. Right, so here the input had 3 entries and the output had 2 entries. So it is allowed for to end up with a vector of smaller size, right? Like here's an example for why this is kind of useful. I mean, this is like a very silly case, but just to give you an idea. You could have had like a vector. So here's another example. Imagine that you have the vector, like a vector in space, right? Like x, y, z. And you want to look at the shadow that the vector makes on the plane. So on the xy plane. So there's a shadow that this vector makes. Is that making sense? What I'm doing? Uh, it's like you had like a light bulb from the z-axis, right? And you just see the shadow that it makes. It like, literally just forgets about the height uh, that this vector had, if you want to think about it with respect to the xy plane, right? And so, if you think like it's not that this like takes a lot of time to write x, y, 0, right? But if you thought about it like in terms of a computer, again, if you keep storing the number 0, that's asking more, you're using more memory, right? To store like the third entry as 0. We know that the entry will always be 0 in this case, right? Because it's going to be somewhere on the xy plane. So you kind of can, just keep track of the first two entries, right? And just call the shadow vector x comma y. So let's call this vector b for shadow, b sub s for shadow, which is just x comma y, right? Because we know the last one is always 0, so why write it down, right? Again, you have to think about it. You're saving money in memory what do you want to be writing 0 every single time? So is there like a matrix, right, that would take this vector and just projected. That's actually the name for this. Like this is called like a projection, and we'll talk about that more late towards the end of the course. But yeah, there is a matrix that does that. It's actually a very easy one. If you take the matrix 1 0 0 and then 0 1 0, you can check. I mean, what is this matrix? Is 2 by 3, right? So you can multiply by a vector x y z, right? Which is 3 times 1. And it does supposed to spit out like the trees, you forget about them, right? So this goes away. So you end up with something which is 2 times 1. And I mean, like, again, everything is either 1 or 0, so it's actually pretty easy to find that it is literally just x, y, right? So, but what I'm trying to say is that it kind of makes sense to like use matrices of different size, because sometimes you just want to, like, in this case, well, it's very obvious that you're storing less information here with the shadow, right? Like you're forgetting about the last entry. So it is like a compression type thing, right? Like obviously, like more interesting processes would be like to compress, like, like compress, like, or forget about information of a vector in a more and interesting way, which is just like, oh, let's just delete the last entry. There are other things you can do, but it's actually this projection is many times like how you solve, like, again, we'll talk about it near the end of the course, like least squares method and other things in experiments like that. Or reducing the size of an image, it actually involves some projection matrix. Just more complicated than this one. But yeah, kind of this. But yeah, it's kind of cool to just, you can start thinking, wow, what operations on vectors, you can represent with matrices and things like that. Like, because like sometimes like it may not be obvious whether or not like a specific instruction can be represented by a matrix. But I think this was just to give you like a sense that it is useful to have multiplications where like the matrix, I mean, this matrix, I'll tell you maybe later. Like this is like a rectangular matrix because the number of rows and columns do not match. Otherwise, it would just be called like a square matrix, which is that's kind of reasonable. But yeah, so rectangular matrices are kind of useful because of that. Okay, so I will talk about a couple of minutes, but I should. Okay, so now that we are a little bit more acquainted with matrices, this is what we'll start doing next time on Wednesday. Well, you can try to do with matrices the same thing we did with vectors, right? So once we had vectors, we talked about how to add vectors together and how to multiply a vector by a number, right? So with matrices, you can kind of do the same. So like, let me just write next time because that's what we'll focus on Wednesday. Oh, by the way, I'll create like another like mini quiz slash assignment on Canvas between Wednesday, just like one where you just do like a matrix multiplication or something like that sort, just to make sure like you tried it on your own before coming again on Wednesday to class. So I'll create it like sometime today, like a mini quiz, like of 1 or 2 questions, like just for you to like do like a product, like one of these multiplications to make sure like everything is making sense. But yeah, so next time what we'll do, like we want to start talking about like adding matrices and multiplying matrices, which actually will be like the part that's a little bit tricky. So adding and multiplying matrices. But like at least I can give you like a heads up of what happens with addition, because like it takes some time to explain that. So if you had like a matrix, like which is, I don't know, like the thing that we have been using before, like the addition subtraction matrix, and now it give you like another matrix which is 1, like 3, -2, 5, right? Well, since they have the same size, the idea is that you are allowed to add them. It will produce a new matrix, and it just ends up being like what you get by adding individually the entries of the matrices. It's kind of the easiest thing you could do. Sorry, A plus B. Like, and I'll repeat this next time. but I just want to give you like a heads up. So like you would do 1 plus 1, that's 2, right? Negative 1 plus 3, that's 2. And then 1 minus 2 is negative 1. And 1 plus 5 is 6, right? So that's what the matrix addition will end up being. So it just will be done entry by entry. And likewise, like you could multiply a matrix by a number or a scalar. So if you wanted to do something like 3a, then you get like 3, negative 3, 3, 3, right? So like the matrix multiplication, like multiplying a matrix by a number will just be multiplying each individual entry by that number. Is that making sense? That's kind of reasonable. Now, what's interesting is how you should like, and this is really what we'll spend more of, like most of next time talking about, like what should A times B be, right? Or B times A. I mean, like actually they'll end up being different, but you could say, well, like in this case, since there are square matrices, maybe you just want to multiply the entries together, right? Like, you know, like do first entry times first entry, the second entry times second entry, third entry times third entry, fourth entry times fourth entry. That actually does not end up being interesting to do. So there's like a reason, like you'll see next time, why that doesn't, like, you wouldn't be doing anything useful if you define multiplication that way. You have to be a little bit more, you know, skillful to see what should like the right multiplication will be. But there will be a way to multiply them, and like the, well, I mean, kind of shocking part will be that this will end up being in general different from B times A, right? So like the multiplication of matrices will be defined in such a way that like the order in which you do it matters, and that's kind of like what makes like linear algebra interesting. Like what like most of the things of linear algebra occur because of that. This thing that the order matters for multiplication. So I'm finishing a little bit early just because I want to finish at the same point as my other class that I'm teaching. So I'll send you an announcement in a couple of minutes. I will have office hours just in case, and I'll upload the video to YouTube and send it as of today, like the summary of what I'm going to say. Yeah.